In this question, you can see that there are two metal chunks. Metal chunks means pieces of metals at different temperatures, and the initial temperature difference between these two is delta T naught. The specific heat of this metal chunk is C1 and specific heat of this metal chunk is C2. They are connected together by a rod of length L and area of cross section S, and its thermal conductivity is K. So we know that as the time will go on, that heat will flow from a metal chunk of higher temperature to the metal chunk of lower temperature. And therefore the temperatures of both of them will change, and hence we have to find out the difference of their temperatures at any time t. So now first of all let us see that for dq amount of heat which flows from this rod, we can say that dq will be equal to delta T, which is the change in temperature, which is the difference of temperature between these two metal chunks, divided by the thermal resistance, which is L by K into S. And this is at any time T, so it is dq by dt. So this is the heat current. Now dq is equal to delta T Ks dt by L. This is the first equation. Now we know that due to this heat dq, the temperature of this chunk is changing by delta T1. So let's suppose its new temperature is T1 and dq will be equal to C1 delta T. So the new temperature is T1 and the older temperature is T01. Okay, now the same heat dq is being given to this C2. So dq will be equal to C2 into we have assumed that the temperature of this chunk is increased. So we have assumed that its final temperature T1 is greater than its initial temperature. So heat is being transferred from this one to this one. Okay, so the temperature of this chunk would have decreased. So its change in temperature will be T02 minus T2. Okay, now you can see that dq by C1 is equal to T1 minus T01. This is equation number 4. And dq by C2 is equal to T02 minus T2. Now this is 5. Now let us subtract equation 5 with equation 4. So this would be, in fact, let us subtract or let us add up these two equations, 4 plus 5. So this will be dq common, 1 by C1 plus 1 by C2 will be equal to T1 minus T2 plus T02 minus T01. So we have assumed that the heat is being flowing from this chunk to this chunk like that, and therefore the greater temperature would be T02. So the temperature difference will be equal to, initial temperature difference will be T02 minus T01. So dq into 1 by C1 plus 1 by C2 will be equal to, this is the final temperature difference between these two, and we can also say that finally the temperature of this chunk is again greater than this chunk. So it can be written as minus of delta T final, and this is plus of delta T naught initial. Okay, so this is the change in temperatures. Now the difference in temperatures. Now let us see that dq was equal to delta T into Ks dt by L. So dq was delta T into Ks dt by L. This was dq, and I am multiplying it with C1 by C1 plus 1 by C2 in this equation. So we can say that delta T into Ks dt by L into 1 by C1 plus 1 by C2 will be equal to, this is delta T naught minus delta T. You can visualize the fact that as heat will transfer from one chunk to another, the temperature difference will keep on decreasing. Therefore, this is the initial temperature difference and this is the final temperature difference. Okay, so we can say that this will be this is the change in temperature difference. I can write that delta T into Ks dt by L into 1 by C1 plus 1 by C2 is equal to d of delta T, change of temperature difference. Okay, and therefore we have to assume that we know that the change of temperature difference should be final temperature difference minus initial temperature difference. So this change is negative because the final temperature difference is lesser than the initial temperature difference. So you can say that d of delta T divided by delta T is equal to minus of L. I am rearranging the equations, that d of delta T upon delta T is equal to minus of Ks by L into dt into 1 by C1 plus 1 by C2. So let us assume that, I am writing it down, that Ks by L into 1 by C1 plus 1 by C2 is equal to alpha. So you can see that if we integrate, then it would be ln delta T, and the limit of delta T will be, initially it was delta T naught and finally it is delta T. So applying this limit delta T naught to delta T, and this is minus Kst by L. In fact, I have assumed it as alpha, so I can write it down as alpha. So this is minus alpha into T. The limit is 0 to T. So delta T is equal to T naught e to the power minus alpha T, where alpha is this one. So this is the difference of temperature as a function of time between these two metal chunks. In this question, you can see that there is a rod of length L which is thermally insulated with the atmosphere, and it is insulated on the lateral surface. Now this rod has a conductivity which is changing with temperature, and the relation between the conductivity and the temperature, absolute temperature, is K is equal to alpha by T, where alpha is some constant. The ends of this rod is kept at temperature T1 and T2, and we have to find out the temperature as a function of x, where x is the distance of a point which is from a first end, which is at temperature T1. So let us assume that there is a rod in such a way such that this rod has a temperature T1 at this end and T2 at this end. The length of this rod is L, and let us assume that there is a small width of this rod dx at a distance of x. So at this point, we know that the current flowing through this rod in steady conditions will be same, or we can say that the current flowing through this rod is same throughout, because the current in series combination is same. So let us assume that at some point of time current I is flowing through this rod. So the resistance of this small element of this rod will be L by Ka, where L is its length which is measured in the direction of heat flow. So its length is dx. So dx by K, which is the thermal conductivity, and A is the cross section area, which I have assumed as A. So this is dx by K, which is alpha by T, and divided by area. This is the resistance. Now the current through this end will be dt. dt is the temperature difference across these two ends of this small conductor. So dt upon dr, which is dx into t divided by alpha A. So this is the current. Now we have assumed that this current is constant throughout the rod at this instant of time, obviously. So we can say that dt by t will be equal to I into dx upon area. So integrating this, we get this is ln t, or you can directly say that initially you can integrate without using the limits. So you can say that this ln t is equal to I upon area into x plus c. C is some integration constant. Now at x is equal to 0, at this end the temperature is equal to T1. So C is equal to ln T1. You can substitute the values. So ln T and ln T is equal to I upon A into x plus ln T1. So I x by A is equal to ln T by T1. First equation. Now again you can say that at x is equal to L, T is equal to T2. So ln T2 is equal to I by A into L into C, which is ln T1. So ln T2 by T1 is equal to I L by A. Now you can substitute the value of I by A from this equation. So I by A is equal to ln T by T1, ln T by T1 divided by x. So this is L by x. Now you can say that ln T2 by T1 is equal to L by x into ln T by T1. So this is ln T2 by T1 to the power x by L, and this is ln T by T1. So, and taking antilog both the sides, you can say that T is equal to T1 into T2 by T1 to the power x by L. This is the temperature of a point which is at a distance of x from this end. Now in the second part we have to find out the current density, heat current density. So from this equation you can see this equation. So heat current density is I upon A, and in this case we have also missed alpha. So this is alpha, and alpha would be with area. So there would be a alpha with area. So this is alpha, and this is alpha, this is alpha, and this is alpha. So the answer would not change in this case. This answer would remain same. But now we know that this is equation number 2. So we know that IL by A alpha, IL by A alpha is equal to ln T2 by T1. So I upon A, which is the current density, is equal to alpha by L into ln T2 by T1. This is the current density. In this question, you can see that there is a uniform cylinder of length L and area S. The thermal conductivity of this cylinder is K, and this cylinder is kept on a metal plate of same area S and mass M, and that plate is of infinite conductivity. the specific heat of that plate is C. You can see this plate, which is represented by this red shaded region, and this top of the cylinder is maintained at a temperature of T0, which is the highest temperature, and the bottom of the plate is at a temperature of T1 initially, and T1 is obviously less than T0. So you can see that heat will flow like that, and therefore we have to find the time which is required to rise the temperature of this plate from T1 to T2. Now first of all, let us write down dq by dt, which is the heat current which will flow through this rod, and this heat current would be L, in fact it would be delta T divided by L and K into S, where K is the thermal conductivity of the rod. So this is heat current, and dq will be equal to delta T Ks dt divided by L. Now this is equation number 1. Now we know that due to this heat dq, the temperature of this surface, this plate will rise, and you can see that dq will be equal to mc delta T. M is the mass, C is the specific heat, and delta T is the change in temperature. So this, in fact, change in temperature of the plate. So let us suppose it as dt. Now this delta T is the difference of temperature of this plate and this top surface. So delta T is T0 minus T. So dq is equal to T0 minus T into Ks into dt divided by L, and this would be equal to mc dt. So you can see that Ks by L into mc dt integration will be equal to dt by T0 minus T integration. Now you can see that the integration of the temperature term would be ln T0 minus T divided by minus 1. Okay, and the limit of this would be from T1 to T2, and on the other side of the equal to, the limit would be from 0 to T, and it would be Ks by LMC. This is Ks by LMC into T, and if I substitute the values of T1 and T2, so it would be ln T0 minus T2 divided by T0 minus T1. It would be equal to minus Ks by LMC dt, and I have integrated this term, so it would be T. So you can see that the time taken by this rod to increase the temperature of this plate from T1 to T2 will be LMC by Ks into ln T2 minus T0 by T, in fact T0 minus T2 by T0 minus T1. Thank you. In this question, you can see that there is a hollow tube of length L, and this tube is having an inner radius of R1 and outer radius of R2. This tube has a thermal conductivity K, and its ends are maintained at the temperature of T2 and T1, and in such a way such that the complete outer end, which is the outer curved surface of this tube, is maintained at temperature T2, and the inner curved surface is maintained at temperature T1, and T2 is greater than T1, and heat is flowing from outside to inside because obviously T2 is greater than T1. So we have to find out the rate at which heat is flowing from outside of the conductor to inside. Now, first of all, let us see that this conductor has a variable. If heat is flowing like that, So the length of the conductor would be this one. Total length would be R2 minus R1, because length is always measured in the direction of heat flow. Now we will face a problem that the area of this cylinder would be variable, because let us suppose that there is a cylinder of radius x. So the curved surface area of this cylinder of radius x will be 2 pi xl. And as we will move from outer part of the cylinder to the inner part, the radius is variable, and therefore the curved surface area is variable. So therefore the cross section area through which heat is transferring from outside to inside is variable, and therefore we need to do the integration. So for integration, let us suppose that there is a thin cylinder of thickness dx and radius x. So the area of cross section of this thin cylinder will be 2 pi x into L, because the length of this thin cylinder would be equal to this L. And we can say that its width is dx, therefore its radius dr will be equal to dx upon k into a, which is 2 pi xl. You can imagine that if heat is flowing through this thin cylinder like that, then its length in which we are using in resistance, that R is equal to L by Ka. So L is that length through which heat is flowing. So heat is flowing from this part in this direction, therefore this length is dx, and the area is 2 pi xl, and K is the thermal conductivity. So the total resistance R will be equal to 1 upon 2 pi k L ln x, and the limit of this would be from R1 to R2. You can integrate in either direction, and obviously keeping in mind that resistance cannot be negative. So R will be equal to 1 upon 2 pi k L ln R2 by R1. So this is the resistance of this cylinder, and therefore the heat current flowing from outer part of the cylinder to the inner part will be delta T upon R, and therefore I will be equal to delta T is T2 minus T1 upon R is ln R2 by R1 divided by 2 pi KL. This is the current which is flowing from the outer part of the cylinder to the inner part. Now we move on the next question. In this question, you can see that there is a hollow spherical shell of inner radius R1 and outer radius R2. It is placed inside a reservoir of temperature 1000 degrees Celsius, which is maintained constant. Now there is some water inside this shell at 0 degrees Celsius, which is the initial temperature, and it is not maintained constant. And the thermal conductivity of this material of the shell is this. Now we have to find out the time required to raise the temperature of this water from 100 degrees Celsius to time required to raise the temperature of the water to 100 degrees Celsius from 0 is this one. So we have to find out the value of K, and the specific heat is given as this and density is given as this. So let us first of all find out the resistance of this shell. So we know that the area of cross section of this shell is variable, and the heat flow will be like that, and therefore the resistance dr of a small elemental shell will be dx upon 4 pi x square into K. K is the thermal conductivity. So the total resistance R would be 1 upon 4 pi K, and this total resistance will be calculated by integrating. So the limit will be from R1 to R2. R1, R2 are the radius. So r is 1 upon 4 pi k, and the integration of 1 upon x square will be equal to minus 1 upon x. So the integration limit would be interchanged by using that negative sign. So r will be equal to 1 upon 4 pi k, and the limits would be 1 upon 0.25, which is 1 by 4, minus 1 upon 0.5, which is 1 by 2. So r will be equal to 1 upon 2 pi k, where value of k is this one. So 1 upon 2 pi, and this is 10 raised to power 2 by 4 pi. So it is 2 divided by 10 raised to power 2. So r will be equal to 2 into 10 raised to power minus 2. Okay, now we see that the temperature, initial temperature of this water was 0 degrees Celsius. And let's suppose that the mass, in fact, we know that the mass of the water is its density into the volume of inner shell, because it is completely filled inside the inner shell. So the volume of inner shell will be 4 by 3 pi r1 cube. So mass will be equal to, density is 10 raised to power 3, you can see that, and this is 4 by 3 into pi into r1 cube, where r1 is the radius, this one. So this is 1 by 4 whole cube. So this is the mass, which is pi by 3 into 10 raised to power 3 divided by 16. So you can say that m will be equal to pi into 10 raised to power 3 divided by 48. Now we know that the temperature, inner temperature of this water, the temperature of this water inside the shell is variable. So let's suppose at time t, the temperature of the water is T degrees Celsius. So at that time, dq by dt, heat current, will be equal to 1000, outer temperature is 1000 fix, minus T divided by R, where R is the resistance. So R is already calculated, which is 2 into 10 raised to power minus 2. So R is 2 into 10 raised to power minus 2. Okay, so this is the, and dq is ms dt, where dt is the change in temperature. So m, we have already calculated the value of m, which is pi into 10 raised to power 3 by 48, or we can substitute it later. So this is ms dt by dt is equal to 1000 minus t divided by 2 into 10 raised to power minus 2. So dt by 1000 minus t is equal to 1 by ms into 2 into 10 raised to power minus 2 into dt, and integrating both the sides. The limit of temperature would be from 0 degrees Celsius to 100 degrees Celsius, and the time would be from 0 to t0. And we have assumed that t0 is the time in which the temperature of water will reach 100 degrees Celsius. The integration of this side will be ln 1000 minus t, and its limit would be from 0 to 100, and integration and divided by minus 1, and integration at that side will be t0 upon ms into 2 into 10 raised to power minus 2. So when we will substitute the limits here, then let us use this negative sign and let us invert the limits. So if we substitute the value 0 at this at the place of t, so it would be ln 1000, and when we will substitute the value of 100 at the place of t, it would be 900, and here it would be t0 upon ms, where m we have already calculated, it is pi into 10 raised to power 3 by 48. And S is equal to this one, 4.2 into 10 raised to power 3. And this is 2 into 10 raised to power 2 minus 2. So T naught will be, this is 24. So T naught will be equal to, this is 10 raised to power minus 4, in fact plus 4 into pi into 4.2 divided by 24 into ln 10 by 9. So we have to find out the value of this 1100k. So if we equate it with 1100k, so you can see that it is given that pi is 22 by 7. So this value is equal to 1100k, and this is pi into 4.2 divided by 24 into 10 raised to power 4. So this is 11k is equal to pi into 4.2 divided by, in fact, we can write it as 420 divided by 24. So the value of k will be equal to pi into 420 divided by 11 into 24. And if we substitute, now we again write down the value of k as pi into 420 divided by 11 into 24. Pi into 420 divided by 11 into 24. And if we substitute the value of pi as 22 by 7, so you can see that this is 2, this is 12, and this is 60, and this will be 5. So the value of k will be 5. So the correct answer of this question will be 5. Now we move on the next question.